Okay, everyone, let us start. Last week, I talked about two concepts. The first one was the effect of the pole location, how the change of the location of a pole or a complex conjugate pole affect the time domain response of a dynamic linear system. And also we talked about time domain specification, how we can justify the time domain response of a dynamic system. The specification we defined, it was time rise, maximum overshoot, peak time, and settling time. And we developed and obtained a mathematical formulation for each kind of specifications. Today, I will talk about two other concepts, effects of zeros and additional poles, because so far we talked about the pole locations of a standard second order system. How about if I have 1 0 or more on the denominator, and how about if I have one more pole on the denominator? How these additional poles or zeros affect the time response or shape of the time domain response of a linear dynamic system. And at the end, I will talk about the stability analysis, how we can analyze the stability of a complex transfer function and without solving or obtaining the poles of the system. So, from the last week, I was supposed to solve an example for you. We have a spring mass damper system. We would like to see how changing the damping coefficient of the system will affect time domain response of the system. Keep in your mind, we have two ways of the controlling of the dynamic systems. We can control them passively or actively. What does it mean, passive control? Passive control means that you tune or you adjust the time domain response of the system by changing the properties of the system. For example, the stiffness, the mass, or damping coefficient. You can actively control a system if you use additional force or an external force to control the system, the performance of the system. Okay, now look at this system, a spring mass system. In order to analyze the performance of the system, we need to obtain or to write the equation of motion of the system. What's the equation of motion of the system? What's the differential equation system that represents the behavior, dynamic behavior of the system? So equation of motion is or are the differential equations that can represent or simulate the actual or real-time behavior of a dynamic system. So, for this simple system, if we write the equation of motion, it will be my double dot, sorry, it's a typo here, my double dot plus by dot plus ky equal to ut. K is the stiffness of the spring, B is the damping coefficient or damping friction, and M is mass of the system. If I want to solve or solve this differential equation or obtain the time domain response, I need to use the Laplace transform. Okay? How can I use the Laplace transform? If you look at the Laplace table, we know that the my double dot Laplace inverse of Laplace of my double dot will be ms squared ys, by dot will be bsys, and ky kys. If I use this one, the Laplace inverse of the ut, Laplace of ut will be us. So the transfer function ys over us will be 1 over s squared plus bms plus k over m. If you compare this transfer function with a standard form of the second order transfer function, you will see 2 zeta omega m is equal to b over m, and omega n squared will be equal to k over m. This one is the omega n squared, and here we have 2 zeta omega n. Correct? Yeah. Is that clear to everyone? So, if I store these two equations, algebraic equations, I can find a relation for the damping and natural frequency. Look, if I solve these two algebraic equations, I have damping ratio equal to B over 2 roots mk and omega n roots of k over m. If you look, both damping ratio and natural frequency of the system are function of 3 parameters: damping coefficient, mass of the system, and stiffness of a spring. Correct? So if I want to achieve, for example, overshoot of 10% or settling time of less than 5 seconds, I can passively control omega n and zeta by changing the characteristic of the system. Correct? So let's give it a try. How we can, for example, the question is that saying the damping coefficient variation. I will change the damping coefficient variation, damping coefficient parameter, and we'll see how the damping ratio and natural frequency will change. As I see, the natural frequency is not function of the damping ratio. Correct? So changing damping coefficient won't change natural frequency of the system, but it will change damping ratio. Correct? Any question? So, look, I will choose 3 values for the damping ratio. B equal to 750 as given in the question. B equal to 1000 and B equal to 1500. If I choose my B equal to 750, the damping ratio will be 0.375, but omega n is constant. It will be 10. If you choose k over m, roots of the k over m will be 10 and will be constant. If I choose B equal to 1000, zeta will be, damping ratio will be equal to 0.5, and for the 1500, damping ratio will be 0.75. And associated poles of the system are given there. From the previous lecture, you can give me some idea how will be the response. If you look at the third one, we have rear part, the larger rear part, minus 7.5. What does it mean?
Stable.
Pardon?
Stable.
No. All are stable because we have the negative rear part.
I agree.
We talked about it last week. If we want to increase the time rise of the system, we need to change or increase the natural frequency of the system. If we want to reduce the settling overshoot of the system, we need to change damping ratio. If we want to decrease the settling time of the system, we need to change minus zeta omega n. Here we have the largest zeta omega n. It means the system will settle down much quicker than 2 others. We have damping ratio for, again, for the third one, highest more than 2 other cases. It means we have less overshoot compared to other cases. Correct? So we have some idea how will be the response. And for all of the cases, it is, just a moment, it is the underdamped system. We have underdamped system. That means we have some oscillations. All rear part are negative. It means that the all cases we have a stable system. Correct? Which means at the final time it goes to the final value. Yeah?
Can you repeat what you said? To increase rise time, increase natural frequency.
Yeah.
What did you say?
And to reduce the maximum overshoot, we increase the damping ratio. And in order to decrease settling time, we need to change the real part of the pulse, which means zeta omega n. I gave you this definition in the last lecture notes. It is in the last lecture. Okay, so let's have a look at the responses. Here is the response. The rise time won't change that much because omega n is constant. But as you see, and as we expected, the maximum overshoot is less, is the most for the zeta, the lowest zeta. And as you see, we have the faster settling or less settling time for the higher, for the third system. Okay? Or for the larger zeta omega n. If you look at the Sutherland, I'm not sure how many of you look at it, but I posted, as I discussed last week, okay, if you look at this system, I developed in Sutherland. Look, you have three options. You can change stiffness, damping, and mass. By changing these three parameters, you can change natural frequency, damping ratio, and real part of the pulse. Let's give it an example. This is the default system. Let's keep mass and stiffness constant, which means we keep constant omega n. And let's play just with damping. If I increase damping coefficient, it means I'm increasing damping ratio of the system. Correct? Because it was B over 2 roots Km. For the first system, for the damping ratio 0.5 Newton meter per second, I have this ratio. This dimension is wrong. I need to fix it. But anyway, if I increase for example to here, look, I don't have any overshoot, which makes sense because I have very high damping ratio or maybe an overdamped system. Let's keep the damping ratio as it is and change the natural frequency. For example, I want to increase, if I change the natural frequency of the system, I will have the more oscillation. Let's change the stiffness of the system. Okay, the damping ratio is too high. Let's decrease it a little more. Okay. Now look, if I increase it more, K of the system, if I increase K, it means I'm increasing the natural frequency of the system. If I increase the natural frequency of the system, I have the faster system. So, but more oscillation. Go at home, take some time and try to play with these parameters and see how the response of the system will change when you change the natural frequency of the system and damping ratio, this damping ratio, by changing the properties of the system. Okay? So, let's get back to again, the equation and the relations we obtained for the raising time, for the maximum overshoot, and for settling time were for the standard second order system. For the more complicated system, we can use duration as a guideline or as a benchmark for the designing the complex system. In other words, we can estimate complicated system by a second order system. But we need to know how this simplification affects the overall performance of the system. Okay? or is it good to estimate a complicated system with the second order system or not, or how much accurate it is? Let's have a look. In reality, we might have some additional zeros, at least 1 0 in numerator. Okay? And we want to see how this 0 will affect the response of the system, or how change the shape of the system, the response of the system. For example, let's assume consider two transfer functions. H1 is 2 over s squared plus 3s plus 2, which is the standard format. If you look, it is omega n squared. Omega n squared is 2, and 2 zeta omega n is 3. And here I have one additional 0. It's exactly the same, one additional 0 in denominator. I have 1.1 as well additional. Why did I add this 1.1 to denominator? Any idea? What's the reason I put the 1.1 here?
Delay?
What?
Delay?
No, not delay. Delay is always shown by exponential function, not for the constant in the denominator. I wanted to make the DC gains of the both system equal. Okay? How can we calculate the DC gain of the system? When put s equal to 0.
Yes.
If I put s equal to 0, here the DC gain will be 1. If I put the s equal to 0, will be 1. This one is 0, 0. 2 will be cancelled with 2, so will be 1. So just for the normalizing the transfer function, it won't affect anything of the response, just this again. To make sure that we have the same this again, I put the 1.1 in denominator of the second transfer function. Okay. If I want to check the step response of the system, I need to find first poles and calculate the use the partial fraction, calculate the constant of the transfer function. What does say this statement? It says there may also be zeros of a transfer function Hs. Okay? At the level of transient analysis, the zeros exert their influence by modifying the coefficients of the exponential terms whose shapes is decided by poles. What does it say? Look, if I use the partial fraction for this, the system transfer function, the first transfer function, I have h1s equal to 2 over s plus 1 minus 2 over s plus 2. If I use partial fraction for the second, if you look at the denominators, poles are exactly the same. So 0 won't affect stability or location of the poles of the system. But if you look at the denominator, for example, s plus 1, I have 2 here. Here I have 0.18. It significantly affects the denominator, the value of the denominator. Not for the, sorry, here I have the minus. But for the second one is 2, 1.64. Not for the pole at minus 2, but for the pole at minus 1, we have a different change. If you look at the poles, I have two simple poles. It means I have the exponential response. Correct?
Yep.
So the shape of the response is the same for the both transfer functions, but the rate is different. If I plot here, look, this is the response of the first system, and here is the response of the second system. As I see, adding 0 to the system or having a 0 to the system, it won't change the shape of the response, but it will significantly change the speed of the response, the swiftness of the response. Is that clear to everyone? Any question? Do you follow? Right, if you have any questions, please ask. Yep.
You said the shape of the game, but
Yeah.
what does change?
The speed of the response. This one is much faster than this one.
Yeah. Yeah, it decreases the rest.
Okay, so we saw how, as an example, how the response will change if I add a 0 to the system. Again, the relations I calculated so far is just for the second order system without any 0. But let's see how the location of this additional 0 will affect the response of the system in general case. The location of the 0. To check that one, I give you a general format of the second order system. I assume I have a 0 at minus alpha zeta omega n. I normalize everything, but based on the omega n, in order to make sure we have the same DC gain compared to the standard format. So I have the one additional pole, a 0, at minus alpha zeta omega n. Zeta omega n is constant. I will change the value of alpha in order to change the location of 0 on S-plane. Correct? For example, if I have alpha equal to 0, it means I have the 0 at origin. If I put alpha equal to 1, I have a pole at minus 0 at minus zeta omega n. Correct? So let's see how the change of this 0, the location of this 0, will affect the response of the system. I have plotted, before that one, if I have a very large alpha, it means here I have a large denominator. Correct? This one is almost 0. And I will have a transfer function close to a standard format. Correct? So, if the location of 0 is far away from the imaginary axis, is a good assumption that I reduce or estimate my transfer function as a standard transfer function. But if alpha is close to 1 or is not that much large, is almost 1, if alpha is almost 1, I can make that assumption. And for sure, it will change the shape of my response. How does it change? Let's have a look at the example. Look, here the brown line is a system without any 0, with no 0. A standard response. If I change alpha from 1 to 20, as you see, for the alpha, it increased both overshoot and time response of the system significantly. Correct? Alpha equal to still is not close to the standard response. But if you look at the alpha equal to 20, is almost the same as a standard system. So if I have a system which its 0 is far away from its pole, it is a good assumption or reasonably accurate assumption to estimate it as a standard second order system and use those relations we obtained for the standard second order system. Correct? Any question?
What is a 0? What?
The roots of the numerator of the system. The roots of the numerator.
So
Okay.
can you repeat again? If the 0 is far away from the root of the
transfer function is a good approximation or is a good estimation to have a standard transfer function or ignore the effect of the zero on the response of the system. Yes?
In what situation do you get the zero?
Depends on your system, physical system. You need to model your system and see if you have the,
So it wouldn't be, it's not when something's false.
pardon?
When there's false vibration.
No, it's not. It depends if you have your input has some derivatives, which is very rare in the reality. But in physics systems, depends on the dynamic of nature of your system.
So the standard system, that would be when you just have the.
Ask your question aloud to other students.
Oh, hold on, I'm not sure yet.
Yes.
See, when you talk about the shape change, it doesn't actually change shape in that.
It doesn't change, just change the estimate or rate of the.
What do you mean when it doesn't change shape? As in it doesn't.
Both are exponential.
Because isn't that becoming more undamped, right?
It's not both the shape of the response are exponential. For example, you don't have the sinus response, right? But the rate of the response is changing.
But isn't it when you underdamp something, you increase the rate to respond to
Yeah, if you have the underdamped system, you have some oscillation, but faster oscillation. You know what I'm talking about? I will show you some examples.
So you are saying this becomes very large, which means this becomes very small. So then you have a 1.
One, you have the standard. This is gain of
So
one.
that's standard, because this again is 1.
One, yeah, exactly.
Good.
Good. So let's see how the zero, adding additional zero will affect the maximum overshoot. If I plot the response of the system or maximum overshoot based on the different values of alpha, as you see, if I have a high damping ratio, the effect of the zero will be neglected or will diminish for the lower value of alpha. If I have a lower or less value of alpha, less value of damping ratio, zero will more effect on the response or maximum overshoot of the system. So in order to damp the effect of the zero on the response, it's good to have the higher damping ratio. Okay? Yes. Alpha is here. Here. I define. Let's this way. Alpha zeta omega n. S equal to minus alpha zeta omega n is zero of the system. I define the parameter alpha to change the location of the zero. Look. So let's, how can I put this on? Okay, look, if this is the S plane, this is the real part, this is the imaginary part. For the standard system, I have two poles. Minus zeta omega n plus omega n root of 1 minus zeta s squared j. And for here, minus zeta omega n minus omega n root of 1 minus zeta s squared j. Correct? And I have a zero here, which its value is minus alpha zeta omega n. These two poles, the location of the poles are constant. But I can change the location of the zeta omega n, the zero, by changing the value of alpha. If alpha is too large, I have a pole here, far away from the poles of the system. If alpha is small, I have a pole near to imaginary axis or near to poles of the system. Okay? That's why I define the alpha to change the location of the zero of the system. What's going to happen? Look, so far I assume I have the positive alpha, and when I have the positive alpha means I have the 0 in left-hand side of the S-plane. Do you have any idea what's going to happen if I have a 0 in right-hand side plane? What's going to happen? Any idea? Let me ask you other way. What's going to happen if I have a pole in the right-hand side of the in the S-plane? Unstable. Exactly. What's going to happen if I have a 0 on right-hand side of the plane?
Same thing.
No. As I said in the previous lecture notes, zeros won't affect the stability of the system, but they affect the response of the system significantly, as we saw. But for this case, if I have the 0 in the right-hand plane, I have this definition. If a system has a 0 in right-hand plane, it is referred to as non-minimum phase system, or non-minimum phase 0.
So, where are you adding the 0 then? Where is it?
The 0 is here. 0 is always in the denominator.
When it becomes very large, so...
Yeah, but here, if I have the 0 in the right-hand side of the complex S-plane, I have a non-minimum phase 0. Any question? So, how does a non-minimum phase 0 affect the response of the system? Let's have a look. Again, if I have alpha, look, for example, the blue line is a standard transfer function, second order transfer function. By increasing alpha, a non-minimum phase 0, the shape of the response will change and it start or initiate in right direction. Instead of having overshoot, I have undershoot. Okay? In general, I don't want to have overshoot. But if you have the non-minimum phase 0, as I said, it won't change the stability of the system. But it causes the system start responding in the wrong direction. Okay? So it's better to avoid non-minimum phase 0 in the system. How on the Earth is possible to have the 0 when you are designing a control? When you are designing a control, you will add a 0 or 4 to the system in order to improve the performance of the system. But if you design your control somehow having a non-minimum phase, you will get the response something like this. Okay? Yep.
How does that response actually look like in real life?
This one?
Yeah.
What do you mean, how does it?
How would it actually like look? No.
For example, it start from this way. If you have the spring damper I show you, you would like to start from the right-hand side, but you start from the left-hand side. And instead of having overshoot, you have the undershoot. Give you a totally wrong direction, which is not desirable. Okay? Any question? Yes?
You talk about a standard system. Is that when S equals alpha, zeta, omega? Or what?
The standard system is this one. The transfer function of the standard system is h of s equal to omega n squared s squared plus 2 zeta omega n s plus omega n squared. Or if you factor out from omega n squared, you will have h of s equal to 1 over s over omega n squared plus 2 zeta s over omega n plus 1. If you factor out omega n squared. So both are the transfer function of the standard second order system. what I'm talking about here, if I have a 0 here, or if I have one additional pole here, how these additional zeros or poles will affect the response of the standard order system. Again, the rising time formulation, maximum peak or maximum overshoot or settling time are calculated based for this transfer function. I would like to see these relations will be valid, if this relation will be valid for the system with additional 0 or additional poles. Okay? We saw from the response, if we have a 0 or pole far away from the complex conjugate roots of the system, this additional pole or 0 won't affect the response of the system. Okay? But if they are close, additional pole or 0, close to complex conjugate poles, for sure they will affect on the system. But we say far away from complex conjugate roots, poles. How far? From this relation, if you look at here, from this, if the real part of additional 0 or additional pole are factor of 6 away from the real part of the complex conjugate poles, they won't affect the response of the system. So if the real part of additional pole or 0 is 6 times of, or larger than 6 times of the actual part or real part of the complex conjugate poles, the system response won't change.
Is that in the notes? Is that in the notes?
Okay. Now we talk about the effect of the additional 0. Let's talk about the effect of the additional pole. How having an additional pole in the transfer function will change the response of the system. Look again. If you ignore this part, this pole, I have a standard transfer function, second order transfer function. But what's going to happen if I have one additional pole? For example, or in another word, instead of having second order system, I have a third order system. How these additional poles will affect on the system? Is it correct or accurate to use this benchmark raising time, maximum overshoot, or settling time formulation I calculated to use for this third order system or not? Can I use those relations for this system or not? Let's see. Again, if alpha is too large, this factor will be goes to 0. So I have almost the second order system. But if alpha is almost 1 or close to 1 or is not that much large, it means this pole will affect on the response of the system. Okay? How it will affect? Let's have a look. Again, this is the standard system, second order system, and here are the responses of the third order system. As you see, by increasing alpha, the response will be close to the second order system. So if the pole of the system is 6 times larger than the poles of the complex conjugate poles, it won't affect the response of the system, and it is a good assumption to ignore this pole and design our system based on the standard second order system. Any question? Comment? Yeah,
You're saying that if alpha is small, then this will affect the.
doesn't affect. The alpha, yeah,
It's
it,
small,
will-
it
yeah,
will
it,
affect.
it will affect.
So
Yeah.
it won't be a second order system.
No, for sure it's a third order system. Still, we can assume, design our system based on the second order system. But we need to have in our mind that the response is not as much as or the same as we expected. For sure, we need to check our design or evaluate our design. Correct? But if it is far away from the complex conjugate of the poles of the system, it is a good assumption that this pole won't affect on the system, on the response of the system. How you can add a how can you add a zero to the system from the year 2 control module? By a proportional derivative controller, PD controller. How can you add an extra pole to the system? Integrator, proportional integrator controller. Okay? So how, first we need to know how these additional poles and zero will affect the response of the system so that I can decide do I need to use the PI controller or PD controller or even PID controller. Right? You need to have a strong view of the response of the system without any controller or the location of poles and zeros in order to have a good design of a control system. When you got expert in the control design, when you see the response of your system, by eyes you can say, okay, I need a PI controller. Let's design a PI controller. Or you can easily say, I need a PD controller. Let's design the PD. Or even PID controller. If you know the time response of the system, how the location of the poles and zeros will affect the response. For example, you see the response of your system is too fast. I want to make it sluggish, so I need to change the natural frequency of the system. How can I change the natural frequency of the system? If you can't change the natural frequency of the system, you can add a zero or pole to the system. Correct? But you need to know what does it mean, the time response. What's the specifications? How the poles location and zero location will affect the time response, or how do them change the response of the system? Okay? As a summary of last week and this week lecture, if we have the standard second order system with no zero and DC gain of 1, rise time will be calculated as 1.8 over omega n. Maximum overshoot MP is e power minus pi zeta over roots of 1 minus zeta square. Peak time is pi over omega d, which omega d is omega n roots of 1 minus zeta square. And settling time Ts is equal to 4.6 over zeta omega n as an approximation of the response of the system. If I have additional zero to the system on the left-hand side of the system, left-hand plane, it will increase the overshoot. The closer zero to the complex conjugate poles, higher overshoot. If the zero is more than 6 times the real part of the complex poles, the effect is negligible. Okay? A zero, non-minimum phase zero or non-minimum phase system, a zero in the right half plane will depress the overshoot and may cause the system step response to start out in the right direction. It means instead of having overshoot, we will have undershoot, which is totally undesirable. We don't want to have such a response. Okay? And as the last additional port in the left-hand plane will increase the rise time significantly if the extra port is within a factor of 6 the real part of the complex ports. Okay, or is not far away from the complex conjugate real parts. Okay, guys. I think you need 10 minutes break. Have a break, wash your faces, and try to prep. We have a more interesting and fun part of the control system next session.